Alright everybody, so welcome back to task sheet on chemical equations. So the first task is to balance the following equations. Now, the reasons we have to balance equations, okay, is due to a law called the conservation of mass. Okay. Now, conservation of mass, and all the conservation of mass states essentially is that mass cannot be created, nor can it be destroyed. Pardon. So if mass cannot be created or destroyed, the number of atoms or ions of each element have to be equal on each side. Okay, so let's have a look at the first one. So we've got one iron, we've got two oxygen atoms, okay, because oxygen is a diatomic molecule. Then we've got iron oxide formed here. Now, iron oxide, there's its constituent ions are Fe and O. Okay, now if you were to have a quick gaze at it, okay, at this question, you'll be able to tell it's not balanced, okay, and that is because we have two oxygens over here and only one oxygen on this side. Okay, so to balance that out, we would place a 2 here. Okay, so in the lesson, you may have heard me say that when you're balancing equations, the best way to do it, okay, is to start to see, to initially see whether your metals are balanced, okay, and then balance the metals first, and then go on to the non-metals. Okay, so that's that. So once we've had a look at this, we now have two oxygens, but as a result, we now have two iron on the product side. So to counteract this and to ensure that the equation is now balanced, we would put a 2 in front of iron, and overall as a result the equation is now balanced. Okay, so when we're balancing and we're putting numbers at the front, putting integers at the front of species, okay, so oxygen, compounds, molecules, or ions, okay, we're multiplying the whole thing by 2. Okay, so we have 2 iron oxide compounds. Okay, so that's that. Now the second one, I'm going to give you an opportunity to pause, okay, and have a go yourself. Okay, so first thing that we always look for is to balance the metals. Now, in this case, the metals are the magnesiums. Okay, so at first glance, they look balanced. Great. Now, we move on to balancing the non-metals. Okay, now, easy non-metal to spot, hydrogen as a part of HCl. Okay, and then hydrogen gas produced on this side. Okay, so we now have two hydrogens on this side, but only one hydrogen on this side. So as a result, what we're going to do is we're going to put a 2 here. Now, this is set off almost a chain of events. Okay, so now we've got two hydrogens here. Okay, but we've also now got two Cls. Okay, and initially we had magnesium chloride, which was made up of 1 Mg and 2 Cls. Okay, now us splitting the two has killed two birds with one stone. We've balanced the hydrogens and we've also balanced the chlorines. Okay, so that is great. Okay, now for those of you who are watching this after the lecture, okay, the lesson, we've got ourselves a polyatomic ion here. Okay, and notice in the lesson I was talking about putting polyatomic ions in brackets when there's more than one of them. Now in this case we have calcium hydroxide, okay, and we've got two OHs. Okay, that is because one OH minus ion, okay, and we also know that calcium is in group 2, so its charge is Ca2+. Okay, therefore to form a neutral compound we would need 2 of these hydroxide ions. Okay, so that's more to do with task 2, task 3, and task 4, but a great introduction. Okay, so now First things first, we have a look at our metals. Are our metals balanced? In this case, yes, they are, because we have one calcium and one calcium here, so that's all good. Now, let's have a look at the non-metals, okay? Let's have a little look at hydrogen. Okay, so we've got two hydrogens here, two hydrogens here, so that's all fine for now. Okay, so the only atom that we haven't looked at is oxygen. Okay, now, if we look at calcium hydroxide, we've got one hydroxide ion, but there's two of them. Okay, so that means we would have two oxygens on this side. Okay, therefore, to balance the oxygens, we'd have to have a look at the reactant side. Okay, and look for the atom or the molecule that has oxygen. Now, in this case, water is the only source of oxygen on the reactant side. Okay, so to balance this oxygen, okay, there's two oxygens here, and to balance it, we'd have to put a 2 here. Okay, we can't just start adding oxygens here and here and here and adding an oxygen molecule, because that would change the equation, and that would go against the law of conservation of mass and just general principles of chemistry, to be honest. Okay, so we put 2 H2O, so now we've got two oxygens on this side, but indirectly what we have also done is now we've ended up with 4 hydrogens on this side, so 2 times 2 gives us 4 hydrogens. Now if we look at this side, we have 2 hydrogens, another 2 hydrogens. Okay, so now we have 4 hydrogen on this side, and again we also have 4 hydrogen on this side, so everything is balanced. Okay, and we've been able to get our balanced equation. Yeah, so balanced equation. Now we'll quickly move over to task 2. Okay, now in the lesson for task 2, well, the part of my PowerPoint that was related to task 2 anyway, I talked about polyatomic ions. Okay, I briefly mentioned that you could classify hydroxide, so OH minus, as one of them. Okay, and I asked you to commit a few of them to memory, so OH minus, so knowing that the charges of these ions. Okay, and then we had nitrate, so NO3. Okay, so our nitrates. Then we also had the sulfates, so sulfate SO4 2 minus. Okay, so remembering these sorts of polyatomic ions. Okay, so ions that are made up of more than one atom or ion. Okay, now the other ones I wanted you to remember were MnO4. Okay, MnO4 2 minus. I also wanted you to remember the carbonate ion. Okay, so just a few ions for you to remember. Okay, so it'd be best if you committed these to memory, because they will help you solve questions like this. Okay, now the first one, the dead giveaway here is you've got yourself a familiar metal. You've got magnesium. Now, what you can do is look at your periodic table and look at what group magnesium is in. Okay, so if you were to have a quick look at your periodic table, you will realize that magnesium is in group 2. Therefore, magnesium would form a 2+ ion. Okay, now if magnesium forms a 2+ ion, okay, and ignoring that I've already told you what the charge of a nitrate is, so here, okay, you would find out the charge of the nitrate, if you hadn't already remembered it, by thinking, okay, so the overall charge of an ionic compound should be equal to 0, because obviously this compound doesn't have a charge, no charge to be seen, and most ionic compounds, well, I'm saying most, all ionic compounds are usually got an overall neutral charge. So in this case, we've got Mg2+, okay, that would mean that the total charge of 2 nitrate ions, so NO3 and another NO3, the total charge of these two would be the equivalent of -2. Okay, so -2, that would give us, sorry, +2, -2, that will give us 0. Okay, therefore each of these nitrate ions, to facilitate this, would have to be NO- and NO-. Okay, so our ions would be, in this case, Mg2 plus, NO3, NO3 minus. And if you wanted to write that out in a more concise manner, you could just say Mg2 plus plus 2NO3 minus. Okay, now you might be asking, how on earth would we get these ions? Well, you put this solid compound, so this salt, into solution and dissolve it and form an aqueous solution, and you'd end up with an Mg2 plus and 2 nitrate ions formed as a result. Now, we can do the similar thing with barium hydroxide. If you look at your periodic table, what you'll notice is what group is barium in? Okay, it's in group 2. And then if it is in group 2, okay, so if you're going back to your GCSE chemistry, it's in group 2, its charge will also be 2 plus. Okay, and hydroxide should be committed to memory that one hydroxide ion has a -1 charge, and as a result, one hydroxide negative, and then also you've got 2 of them, which minus. You could also apply the same principle that we applied here to figure out what a nitrate ion is, okay? But it's better to commit these sort of ions, OH minus, essentially to memory. Okay, so we would have, this would form 2 hydroxide ions and a barium. And again, we can just write it out as before. Barium 2 plus 2 hydroxide ions. Okay, I'm going to pick up the speed a bit, okay, and we're going to try and chug along, okay. So Na2CO3, okay, again, sodium is in group 1, so it's going to have a +1 charge, and we've also got 2 of them, so another sodium. Okay, now, if the overall charge of these would be +2, the overall charge of the carbonate should be -2, to ensure that the overall charge of the ion is 0. Of the compound is 0, the ionic compound. Okay, therefore we could just put CO3 and we could put 2 minus, and there's your answer. Okay, so sodium, we have 2 of them plus our carbonate ion, and that would give us our answer for that. Again, copper oxide. Now, what you'll notice, for those of you who have been reading ahead or are just generally curious in chemistry, okay, you'll see a metal, then you'll also see Roman numerals in brackets. Now, all these Roman numerals mean, they're actually doing your solid, is that they're telling you what the charge of the resultant this metal is. Okay, now, for those of you who can see this question, you might be thinking, well, we've got copper 2 oxide. How can the same metal essentially form 2 different charged ions? Okay, this is due to copper being a transition metal. Okay, and we'll learn more about transition metals, and this property is called something called variable oxidation states. So transition metals, one of their main properties is they have variable oxidation states. Now, for now, all you need to know is that the brackets are indicating the charge of the ion or the metal. Okay, so if it's, you can read it as copper 1 oxide. Okay, so if it's copper 1 oxide, you're forming copper 1 ion, so Cu1 plus. Okay, and from the formula you can see we're forming 2 of them. And the fact that we know that the overall charge of an ion, so these 2 would give us a collective charge of +2. Okay, so the overall ion has to form, the overall compound has to form something that's neutral. So from that we can tell, okay, so oxygen would have to have a -2 charge. Okay, so we can put 2 minus. Okay, for those of you who are noticing, I put the number first, so the integer first, and the charge after. Okay, that's just good practice that all chemists should be in. Okay, so this is the way we write charges. We don't write the number first and then put, we don't write the sign first and the number like we do in maths. We do the opposite way, okay, because we like to be special. but that's just the way we do it in chemistry. Okay, so from that you should be able to write down the constituent ions. So we would have 2Cu plus O2 minus. Okay, again, whenever we're doing this, we need to ensure that the overall charge of these two ions when they're added together is 0. Okay, now copper 2 oxide, a bit more of a simple story. So copper 2, so it would be Cu2 plus, and then the oxygen, the charge would be 2 minus. Okay, so the overall charge would be equal to 0. So we would have copper 2 plus plus O2 minus. Okay, and last but not least, lead oxide. Okay, so again, we've got lead IV. Okay, for those of you who are not well versed in the Roman numerals, IV is 4. Okay, so I'd encourage everyone in this class to learn your Roman numerals 1 through 10. Okay, so lead 4 oxide. So it's easy to guess. Lead, what charge is it going to have? It's going to have a plus 4 charge. Okay, a 4 plus charge. And we've got 2 oxides, so O. And because we know the overall charge has to be 0, and the fact that we've used oxide in the previous 2 examples, we know it's 2 minus, and that would give us an overall charge of 0. And these are our constituent ions. Okay, so from that we should be able to get our answer of Pb4 plus 2O2 minus. Okay, so that's that. Now let's move on to task 3. Okay, so determining the balanced ionic equation from the word equations below. Now, first things first. Okay, I've probably made a song and dance about this in the class. Balanced. Okay, whenever you see an equation, you have to see, or you have to observe whether it's balanced or not. Okay, so if an equation isn't balanced, the first thing you should be doing is balancing it. Okay, and then what you'll notice as well, we're getting a balanced ionic equation. Okay, ionic equation, as the name suggests, is when we have ions. Okay, so at GCSE you probably were used to having sort of displacement reactions and not ending up with ions. Okay, now all of these examples below are essentially forming aqueous solutions. Okay, so AQ, 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 AQ. Okay, so all it is taking these 4 salts and dissolving them in water and forming a solution. Okay, now anything that's in solution has the state symbol of aqueous. Okay, or aqueous for some of our southern friends. Okay, so that's all aqueous means, it's in solution. Okay, and what I've also probably told you in class is that if we have a solid species, so anything with the state symbol S, we don't write them out as ions. Okay, so we don't write it out as ions. Anything that is aqueous, okay, we write out as ions. Okay, anything that is gas or gaseous, okay, we don't. Yikes, that handwriting is bad. We don't write the gas out in ion form. Okay, so if you see H2O gas, that's not your sign to say, okay, we're going to have 2 hydrogens and an oxide. We wouldn't do that because that's not what it is. Okay, But then if we see another species as liquid, okay, liquid is not the same as aqueous, so if you see a liquid, don't write it out in its ion form, so don't write them out as ions. Okay, so that's also in the don't category, so don't write it out as ions. Okay, so that's that. Now let's shift our attention back to task 3. Okay, so shifting our attention all the way back to task 3. Now, what we can do now is firstly find out, well, we should already know, but we should find out the formula of magnesium bromide. Okay, now we know that Mg is in group 2, so it's going to have a 2 plus charge. And we also know that bromine is in group 7, so the resultant bromide ion would be have a -1 charge, because if it's in group 7, it needs to gain an electron to have a fall out of a shell. Okay, so all that hoopla from GCSE. Okay, now the fact that one bromide ion has a charge of -1 and magnesium has a charge of +2, that means we would need 2 bromide ions to balance this magnesium out. So some of you probably have already guessed the formula is MgBr2. Okay, and that forms magnesium ions, which we've already identified as +2. If magnesium was going to form an ion, it would be +2 because it's in group 2. And then a bromide ion is Br minus. Now, if we quickly look at that, okay, when we were looking at ionic equations, my two main concerns were, is it balanced? Okay, that was one of my main concerns, is it balanced? And number 2 was, is the charge on the reactant side equal to the product side? So these are the 2 questions you should be asking yourself for every question you do, especially in the sciences. Okay, so you should always be questioning yourself. But in this case, for when we're balancing ions, is it balanced? Is the charge of the reactant side equal to the product side? So if we have a look at this first, we know that the charge over here is 0. But then we have a charge here of 2 plus 1 minus, which gives us +1. So if the charge over here is 0 and the charge over here is +1, is it balanced? No. Is the charge balanced on the reactant to product side? No. Are the atoms and the ions balanced? Okay. Are we ensuring that the law of conservation of mass is being maintained? From the looks of it, we have one magnesium. The magnesiums are fine. We have 2 bromide ions over here, but we only have 1 here. So to ensure that it's balanced and the charges are equal on both sides, we place a 2 in front of the Br. And what we end up with is 2 times -1, that gives us -2, +2 over here, so -2, +2, and then an overall charge of 0, and then the overall charge over here is also 0 because +2 and -2 cancel out. Charges are balanced on both sides, so overall charge here is 0 and the overall charge here is 0. So we're definitely correct in terms of part 2, well, question 2. And is it balanced? Yeah, we balanced it. Okay, now for those of you who didn't complete this in class, I'm going to give you a 5-second pause where you can pause and attempt each question. Okay, so that should be enough of time for you to have paused. Okay, so aluminium nitrate. Okay, now nitrate was another ion I wanted you to commit to memory, so it was NO3 minus. Okay, and aluminium, okay, the charge of aluminium is +3. Okay, you're gonna have to become very familiar with aluminium. It's part of a lot of catalysts that you're going to use next year in year 13, hopefully, for those of you who are sticking around. Okay, so if the charge of one nitrate is minus and the charge of one aluminium ion is +3, we're going to need 3 nitrates to balance this out, okay, to get an overall neutral charge. Okay, so the formula of an aluminium compound, or aluminium nitrate compound, is AlO, Al brackets NO3. Okay, see how I put the polyatomic ion in brackets? Okay, it's always good practice. And as we said, we need 3 of them, so I put 3. Okay, now here's the easy bit. The hard bit is actually finding out the initial formula. Okay, so it goes and it forms aluminium ions. We know that aluminium is going to be a +3 ion. Okay, so Al 3 plus. Okay, and what I've been doing, I haven't been putting my state symbols. We really need our state symbols, guys. State symbols are where some silly marks are lost. Okay, so that's a solid. This is also a solid. This is aqueous. Okay, and then nitrate, NO3. That's also aqueous. Okay, now we've got our equation. Okay, but we're going to ask ourselves the same questions before. Is it balanced? Well, we've got 3 nitrates over here and 1 aluminium. We've got 1 aluminium, so the aluminium is balanced, but we only have 1 nitrate here on the product side. So what we're going to do is we're going to place a 3 in front of it, okay, just to match up the nitrates. Okay, so it's balanced, but are the charges balanced? So the overall charge here, because we've got a compound, is 0. Okay, and the charge over here is +3. And because we've got 3 lots of negative nitrates, the overall charge over here, the total charge of the nitrates is -3. And that would overall give us a charge of 0 on the product side. And the overall charge on the reactant side is also 0. Okay, so the charges are balanced and the overall equation is balanced. So this is our answer. Okay, so in the exam, you don't need to show that it's balanced or the charges are balanced. This is just for your own peace of mind. Okay, that you've got your equation right, you've got everything. You've ticked all your boxes essentially. Okay, but with practice, it will just become second nature to you. Okay, now iron chloride. Okay, I haven't actually specified what charge of iron what the charge of iron is, because iron is also a transition metal. It's found in your D block. Okay, so what I'm going to do is I'm going to say that it is iron 3. Okay, so iron 3 is just the 3 I's, okay, in Roman numerals, so it's iron 3 plus, so iron 3 chloride. Okay, so if it's iron 3 chloride, we would have Fe. Iron would have a +3 charge. Okay, so we also know that chlorine forms chloride by gaining 1 electron because it's in group 7. Chlorine is in group 7. So it would have a -1 charge for each each chloride. So we need 3 chlorides to balance 1 iron. So it'd be FeCl3. And again, it's a solid, and that would go to form ions. Okay, so that's a nice little tongue twister for you. Say that about 5-10 times. I guarantee you won't be able to say it. Okay, so Fe. Okay, they've told us, they've been very nice, or I've been very nice after correcting myself. Iron 3. Okay, so iron 3 plus, aqueous, and chloride ions, so Cl minus. Okay, then we're going to ask ourselves the same questions as we did before. Is it balanced? Let's have a look. So we have 1 Fe, looking good. Cl, we've got 3 of them, but wait, we've only got 1 Cl over here. So the logical thing to do is place a 3 in front of the Cl so that the Cl's are balanced. Now we do our last check. Is the charge on the reactant side equal to the product side? Let's have a look. So 0 plus 3. Okay, so we've got an overall charge of 0 on this side. Okay, and the charge in the iron is plus 3. The overall charge of the 3 chloride ions is -3. So as a result, we have a overall charge of 0 on the product reactant side, and we have an overall charge of 0 on the product side. So yes, our 2 questions that we ask ourselves, we've met them. And this is our overall ionic equation. Okay, good. Now, here we've got copper 1 oxide. Okay, so copper 1 oxide would mean that we would have Cu plus so 1 plus. Okay, and an oxide ion, as you probably have committed to memory by now, is -2. So to balance this out, we would need 2 coppers for every 1 oxide. Okay, so the formula would be Cu2, so 2 coppers, oxide. Okay, now then we form copper ions. Okay, but because we've already been told it's copper 1, we're going to have copper 1. Okay, now then oxide. Now oxide has a charge of -2, so 2 minus. Okay, so then we're going to ask ourselves the question that we've always asked ourselves, the 2 questions. Is it balanced? Is it balanced, guys? So we have 1 oxygen, 1 copper, we have 2 coppers and 1 oxygen. Okay, so definitely we need to balance the coppers. So 2 coppers, we're going to do the sensible thing. Place 2 Cu pluses. Okay, so the overall charge now, we need to have a look at the overall charges, so question 2. So we'd have an overall charge of +2 here for the coppers, and obviously a -2 here for the singular oxide ion. And the overall charge here is 0. So collectively, the total charge on the product side is equal to 0 because the +2 and the -2, they cancel each other out. And collectively on the product reactant side, it's a charge of 0. So yes, we satisfied these 2 questions. And we've given ourselves peace of mind that yes, indeed, this is our final ionic equation. So for those of you who are still watching, we're about 32 minutes deep. And congratulations, you really love chemistry. Okay, so now the real crux of the matter, task 4. Okay. Now, I have been quite nice, and I've given you an example in your task sheet. Okay, so the step 1 was always to write out the equation in terms of ions. So this was following what we did just recently now in task 3. Okay, so we wrote our equation. Okay, then what I've done is wrote the equation out. Okay, so this subsequent equation in terms of ions. Now, what you'll notice is when I formed a solid, I haven't wrote out the ion form of it. I've left it as Fe. But when we've got an aqueous species, we have to write out that compound in its subsequent ions. Okay, so what I've done is I wrote out copper 2 plus and I wrote out sulfate, SO4 2 minus. Then again, on this side, we've got iron sulfate, and again, it is aqueous. So if it's aqueous, we write it out in its substituent ions. So Fe2 plus and 1 sulfate ion. And then what you'll notice again is copper is solid, so we're just going to leave it alone and just write it as copper because it hasn't been dissolved in solution, it's not in solution, so it hasn't formed any ions. Then we go to step 2, and that's where we cancel out the ions that appear on both sides. Okay, now we have sulfate, so SO4 2 minus appearing on the product side, we have 1 appearing over here. So for every sulfate that appears here, we can cancel out 1 sulfate that appears here. Now, quite nicely for us, we've only got 1 sulfate here and 1 sulfate here, so we can just cancel them out. Okay, and then whatever we're left with, that would give us our final ionic equation, which is here. Okay, now for those of you who are feeling a bit brave, you could tell me during the lesson or after the lesson when you see me next what's being oxidized and what's being reduced. Okay, that'd be really cool. Okay, I'll leave that with you. Maybe you want to remember your oil rig. Okay, so if you could just tell me what's been oxidized, what species has been oxidized and what species have been reduced. Quite impressed. Okay, and it would give me a little hint that some people are actually watching my videos. Okay. Okay, so determine the ionic equations from the following equations. Okay, now state symbols are key here, guys. They're going to tell us what we have to do. Now, HCl is aqueous. Okay, so HCl is aqueous. And if HCl is aqueous, we're allowed to write it out in its ion forms. Again, NaOH, aqueous, we can write it out in its ion form. NaCl, aqueous, we can write it out in its ionic form. Now, H2O is liquid. Okay, liquids we can't write out in their ionic form. So, no, yes. Okay, so no, we can't write it out in its ionic form. Liquids, gas, solid. And then aqueous are the only ones where we can write them out in their ionic forms. They're fair game. Okay. Now, the first thing we have to do when we're looking at ionic equations is always to check whether the equation is balanced. Okay, you're probably tired of the word balance by now, but it's really important. So let's have a look. Is this equation balanced? Got one hydrogen here, and then we've got two hydrogens here. So hydrogens are balanced. Got one sodium here, so sodiums are balanced. We've got one oxygen, it's fine. Cls are balanced, Nas are balanced. Okay, so this equation is balanced. Okay, so now we're just going to have a look at what ions are formed on the reactant side and what are present on the product side. Okay, so we can write out HCl in its ion form, so it's H plus Cl minus. Okay, and then we can have a look at our sodium hydroxide, which is Na plus. Again, sodium group 1, so +1 ion. OH minus. Okay, another one that you should have committed to memory. And that's all the things that we have, all the ions that we have on the reactant side. Okay, for those of you who are this deep into the video, I don't think you need reminding, but reactants, products, I really should have reiterated that at the start. Okay, NaCl. Again, it's aqueous, fair game, we can write it out. So Na plus Cl minus. And then water is liquid, so we're just going to leave it as good old water. Okay, because we're not writing in its ionic form, because we don't write liquids, gases, or solids out in their ionic form. We only write aqueous in their ionic forms. So from that, what we should be able to do now is look at both reactants and products and start crossing out ions that appear on both sides. Okay, so one Cl minus appears on the product side, one Cl appears over here, so we're going to cross them out. Okay, one sodium appears here, one sodium appears here, so we're going to cross one out, each from each side, one from each side. And what you'll notice is we're now left with H plus OH minus, giving us H2O. Okay, and then we can just jot in our state symbols, so liquid, aqueous. Okay, so Bob's your uncle there. Okay, nice, simple, easy one to get us started. Okay, now we're moving on to barium chloride, and sodium sulfate goes to sodium chloride and barium sulfate. Now, again, we look at our state symbols. Aqueous, yes, we're writing out this barium chloride in its ionic species, ionic form. Again, aqueous, ionic form, great. Aqueous, ionic form, solid, no. We're going to leave it as is. Okay, no, we don't write solids out in their ionic form, we don't write gases out, and neither do we write liquids out. Okay, so first things first, is this equation balanced? Okay, short answer is no, it's not balanced. Okay, so you might be thinking barium, the metal, yep, balanced. Sodium, the next metal, is it balanced? No. We've got two sodiums over here, only one here, so the logical thing to do is stick a big 2 in front of sodium chloride. And as a result, we've got two sodiums, two chlorines, two sodiums, one sulfate, one barium. So yeah, now the equation is balanced and we can go ahead and write out our ionic equation. Now, barium chloride is Ba2+, because barium appears in group 2. And then we've also got Cl2. Now, What I am going to do initially is write out the two Cl minus ions that we get from this separately, okay, just to make it clear what we're forming, okay. But otherwise, what you would see is something different when you're actually doing the questions and in some examples, okay. And I'll try and if you were paying attention in class, I would have shown you how we actually do it. But I think for this purpose of showing the cancelling out, it'll be best if I write out two Cl minuses like this, so Cl minus and another Cl minus. Okay, then we move on to sodium sulfate. Okay, so we're going to have Na plus, another Na plus, because there's two sodiums here, and a sulfate ion. Okay, so that's all there is there. Okay, and that is giving us 2 NaCl. Okay, as we know, when we're balancing, if we put a big number at the front, we're multiplying everything through by 2. Okay, so we're going to end up with 2 Na pluses, and we're also going to end up with 2 Cl minuses, and we're going to end up with a barium sulfate because it's solid and we don't write it in its ionic form, so it's BaSO4. Okay, now here comes the fun bit, cancelling everything out. Now let's start with barium. Got one barium here, no other barium ion on this side. We've got barium sulfate, but no barium 2 plus ion on this side, so there's nothing to cancel out. Then we have 2 Cl minuses here. Okay, so for each, we also have 2 Cl minuses here. So for each ion that we cross out on this side, we'd have to cross out another Cl minus on this side. Okay, so I'm going to cross out one here, one here, one here, one here. Okay, now then we move on to sodium. So we've got 2 sodiums here and 2 sodiums here. So for each sodium ion we cross out on this side, we have to cross out one on this side. The same thing again. So 1, 2, 1, 2. And what you'll notice is we are left with barium 2 plus sulfate and the resultant barium sulfate ion compound. Okay, so the overall equation here again would just be barium 2 plus all aqueous plus sulfate SO4 2 minus. Aqueous goes to barium sulfate solid. Okay, so we're nearly there. One more to go. Okay, so this is the trickiest of them all. Sodium carbonate goes to nitric acid. Sodium carbonate plus nitric acid goes to form sodium nitrate plus water plus CO2. Okay, first things first, we have a quick little look through what we're going to write in ionic form. So aqueous, yes, we're going to write ionic form. HNO3, aqueous, yep, you bet. We're going to write it in its ionic form. Sodium nitrate again, aqueous, so we're going to write it in its ionic form. Liquid, no, we're just going to leave it as H2O because we don't write liquids as ionic species in their ionic forms. Okay, and again we have a gas which we don't write in its ionic form. Okay, so now we've had a quick look through just what we're going to write out in its ionic form and what we're not going to. So the second thing we have to look through now is this equation balanced originally to start with? Okay, so as we always do, let's start with the metals. So we've got 2 sodiums here, and on the product side we only have 1 sodium. So to balance that, we're going to put a 2 here. Now, as a result of that, what we've now done is we've ended up with 2 sodiums, but we've now also ended up with 2 nitrate ions. Okay, because we've ended up with 2 nitrate ions, what we're going to have to do is get more nitrate on the reactant side, and the only source of an NO3 is this nitric acid. So because we have 2 nitrates here, we're going to have 2 nitrates here to balance it out because that law of conservation of mass. And as a result, what we have now is this overall equation. And if my maths is correct, this equation is balanced. So 2 hydrogens, 9 oxygens, and yes, another 9 oxygens. So yes, it is balanced. Okay. Now, This is a long one, so strap in, guys. Okay, so we're going to start from the left, writing it out in its ionic species, writing it out in its ionic form. So Na plus, how many of them do we have? We have 2. Then we have a carbonate, which is 2 minus. Then we have 2 H pluses coming from the NO3, HNO3. Then we have 1 nitrate, 2 nitrates, 1, 2. Okay, that gives us 2 sodium nitrates, sodium. Okay, so you can see the long list of ions that we have. Okay, and then we have our NaNO3s. We have 2 sets of them. So okay, so I'm kind of running out of space, but now we have liquid and gas, so we don't write them out in the ionic form. We just leave them as normal, H2O plus CO2. So we're going to start cancelling stuff out now. Okay, so we have 2 NAs on this side and 2 NAs on this side. So 1, 2, 1, 2. Okay, so the NAs are cancelled. Then we have 2 NO3 minuses here, so 1, 2, and we're going to cancel out the same number of NO3s on the product side, just to make it a bit clearer, because I haven't made it too clear. This is the products, this is reactants, either side of the arrow. Now, have we got any other ions that we can cancel out? I don't think so. We've got a carbonate and 2 hydrogen ions left over, and water and carbon dioxide on the other side. So our final equation is just going to be a simple matter of now just writing down what we have and what we don't have. So we have CO3 2 minus, aqueous as always, plus how many hydrogens do we have? We have 2 hydrogen ions, so 2H plus, aqueous, all going to H2O plus CO2 with their state symbols, so liquid and gas. And there we go, guys, we've got our final product. Okay, so hope this has been helpful. If there are any more questions, feel free to ask me those questions, and I will see you in the next walkthrough. Take care.